What if everything you see, touch, and experience is actually a sophisticated simulation running on advanced computational hardware far beyond our comprehension? This isn't just science fiction anymore. The simulation hypothesis, seriously considered by philosophers like Nick Bostrom and physicists, including Nobel laureate George Smoot, suggests that our reality could be artificial, a digital construct created by some advanced civilization. We can already create entire universes inside computers, complete with their own physics, galaxies, stars, and even the potential for life. If we can do this with our relatively primitive technology, what might a civilization millions of years more advanced be capable of? And if such simulations are possible, how can we be certain we're not living in one right now? Scientists around the world are using the most powerful supercomputers ever built to run extraordinarily detailed simulations containing billions upon billions of particles, each following the fundamental laws of physics. After all, we can't watch a galaxy form in real time, but in a simulation we can witness the entire cosmic story unfold, from the earliest moments after the Big Bang to the present day. These simulations represent incredibly powerful scientific tools because of a fundamental limitation we face as cosmologists. We only have one universe to study, our own. We can't rewind time to see how it all began. We can't run experiments where we change the laws of physics to see what happens. But in a simulation, everything changes. We gain the power to conduct true experiments on entire universes. We can adjust the amount of dark matter and see if galaxies still form properly. We can change the rate of cosmic expansion and watch how that affects the large-scale structure of space. It's like having a cosmic laboratory where we can test our theories against countless possible realities. Here's how researchers create these digital universes. They start with initial conditions representing the early universe. Into this digital cosmos, they input the fundamental forces: gravity, the properties of dark matter, the expansion rate of space, and the behavior of ordinary matter. Then they press start and the simulation begins to run, calculating how, over the course of the simulation, the universe evolves from a nearly uniform sea of matter into the magnificently structured cosmos we observe today. Galaxies form from collapsing clouds of gas. Vast filaments of matter stretch across hundreds of millions of light years. Connecting galaxy clusters between these filaments lie enormous voids, creating the foam-like structure of the cosmic web. The simulation begins with initial conditions representing the universe just a few 100,000 years after the Big Bang, tiny density fluctuations of about 1 part in 100,000. These fluctuations provide the seeds from which all cosmic structure will eventually grow. Without these initial ripples would no stars, no galaxies, and no life. Scientists then input the fundamental constants that govern our universe: the density of dark matter, which provides the gravitational scaffolding for structure formation; the cosmological constant, which controls cosmic expansion and dark energy; the density of ordinary matter. In the initial expansion rate, even small changes can produce dramatically different cosmic outcomes. Then the simulation marches forward in time, step by computational step, calculating the evolution of the universe moment by moment. Denser regions exert stronger gravitational pull, small fluctuations to grow exponentially over time through gravitational instability. This amplifies those tiny initial fluctuations by factors of millions. Dense regions eventually collapse under their own gravity and fragment, forming the first stars and galaxies when the universe was just a few 100 million years old. The simulation tracks all of this, following billions of particles as they move through space, clump together, and build the cosmic structures we see today. These simulations must incorporate several key components of physics to accurately reproduce our universe. First and foremost is gravity, the attractive force between all matter that drives cosmic structure formation. Then there's dark matter, the mysterious invisible substance that makes up about 85% of all matter in the universe. We can't see dark matter directly because it doesn't emit, absorb, or reflect light. Dark matter forms the invisible gravitational scaffolding upon which ordinary matter can collapse to form galaxies. Without dark matter's extra gravitational pull, galaxies as we know them simply couldn't exist. In simulations, dark matter particles are typically treated as collisionless, meaning they pass right through each other, interacting only through gravity. Scientists around the world are using the most powerful supercomputers ever built to run extraordinarily detailed simulations containing billions upon billions of particles, each following the fundamental laws of physics as we understand them. These aren't simple models or approximations. They're comprehensive computational universes where every particle interacts with every other particle through gravity, where gas clouds collapse and heat up, where stars form and explode, and where galaxies collide and merge. These computational models help us understand cosmic evolution and answer questions that would be impossible to investigate through observation alone. After all, we can't watch a galaxy form in real time. That process takes billions of years. But in a simulation, we can witness the entire cosmic story unfold, from the earliest moments after the Big Bang to the present day, and even peer into the distant future. These simulations represent incredibly powerful scientific tools because of a fundamental limitation we face as cosmologists. We only have one universe to study, our own. We can't rewind time to see how it all began. We can't run experiments where we change the laws of physics to see what happens. We're stuck observing a single cosmic history that has already unfolded. But in a simulation, everything changes. We gain the power to conduct true experiments on entire universes. We can adjust the amount of dark matter and see if galaxies still form properly. We can change the rate of cosmic expansion and watch how that affects the large-scale structure of space. We can modify fundamental forces like gravity, making it stronger or weaker, and observe the consequences. We can even explore completely alternative physics to see what kinds of universes are possible. All of this happens over billions of simulated years, compressed into months of computation. It's like having a cosmic laboratory where we can test our theories against countless possible realities. Here's how researchers actually create these digital universes, step by step. They start with initial conditions representing the early universe, just moments after the Big Bang when the cosmos was incredibly hot, dense, and remarkably uniform. Into this digital cosmos, they input the fundamental forces and properties that govern reality, gravity and how it causes matter to attract other matter, the properties of dark matter and how it clumps together, the expansion rate of space itself and how it changes over time, and the behavior of ordinary matter, the atoms and molecules that make up stars, planets, and everything we can see. Then they press start, and the simulation begins to run, calculating the gravitational forces between every particle, updating positions and velocities, tracking how gas heats and cools, following the formation of structures. Over the course of the simulation, the universe evolves from a nearly uniform sea of matter and energy into the magnificently structured cosmos we observe today, with its intricate cosmic web. Galaxies form from collapsing clouds of gas drawn together by gravity. Vast filaments of matter stretch across hundreds of millions of light years, connecting galaxy clusters like a cosmic neural network. Between these filaments lie enormous voids, regions nearly empty of matter, creating the foam-like structure of the cosmic web that defines the large-scale architecture of our universe. The simulation begins with initial conditions representing the universe just a few 100,000 years after the Big Bang, during an era known as recombination, when the universe had cooled enough for atoms to form. At this point, the cosmos was remarkably smooth and uniform, but not perfectly so. There are tiny density fluctuations, regions where matter is slightly more or less concentrated than average, variations of only about 1 part in 100,000. These fluctuations, predicted by inflationary theory, provide the seeds from which all cosmic structure will eventually grow. Think of them as the cosmic DNA that determines where galaxies, clusters, and voids will eventually appear. Without these initial ripples in the density of matter, the universe would have remained forever smooth and featureless, with no stars, no galaxies, and no possibility of life. These fluctuations are so important that we can actually observe them directly by studying the cosmic microwave background radiation, the afterglow of the Big Bang, which shows us a snapshot of these density variations imprinted on the sky. Scientists then input the fundamental constants that govern our universe, the precise values that determine how reality behaves. These include the density of dark matter, which provides the gravitational scaffolding for structure formation. They input the cosmological constant, which controls cosmic expansion and the mysterious dark energy that drives it. They specify the density of ordinary matter, the atoms that will eventually form stars and planets. They set the initial expansion rate of the universe, known as the Hubble constant. Each of these parameters must be carefully calibrated based on our best observations of the real universe, because even small changes can produce dramatically different cosmic outcomes. Then the simulation marches forward in time, step by computational step, calculating the evolution of the universe moment by moment. Denser regions, where matter is slightly more concentrated, exert stronger gravitational pull on their surroundings. This causes small fluctuations to grow exponentially over time through a process called gravitational instability, where the rich get richer and the poor get poorer. Dense regions attract more matter, becoming even denser, while less dense regions lose matter and become voids. This runaway process amplifies those tiny initial fluctuations by factors of millions. Dense regions eventually collapse under their own gravity and fragment into smaller pieces, forming the first stars and galaxies when the universe was just a few 100 million years old. The simulation tracks all of this, following billions of particles as they move through space, clump together, and build the cosmic structures we see today. These simulations must incorporate several key components of physics to accurately reproduce our universe. First and foremost is gravity, the attractive force between all matter that drives cosmic structure formation. Gravity is computed using sophisticated algorithms that calculate forces between particles efficiently, because computing the gravitational interaction between billions of particles and every other particle would be computationally impossible using brute force methods. Then there's dark matter, the mysterious invisible substance that makes up about 85% of all matter in the universe. We can't see dark matter directly because it doesn't emit, absorb, or reflect light or any other form of electromagnetic radiation. It's completely invisible to telescopes. Yet we know it exists because of its gravitational effects on visible matter, on the rotation of galaxies, on the motion of galaxy clusters, and on the bending of light from distant objects. Dark matter forms the invisible gravitational scaffolding upon which ordinary matter, the atoms that make up stars, planets, and us, can collapse to form galaxies. Without dark matter's extra gravitational pull, galaxies as we know them simply couldn't exist. The visible matter would be spread too thinly to collapse and form stars. In simulations, dark matter particles are typically treated as collisionless, meaning they pass right through each other, interacting only through gravity. These simulations must incorporate several key components of physics. First, there's gravity, described by Einstein's general relativity, where mass and energy curve space-time itself. Scientists around the world are using the most powerful supercomputers ever built to run extraordinarily detailed simulations containing billions upon billions of particles, each following the fundamental laws of physics we've discovered. These aren't simple animations or visualizations. They're genuine digital universes that evolve according to the same rules that govern our cosmos. These computational models help us understand cosmic evolution across billions of years, test competing theories about mysterious dark matter and dark energy, predict the ultimate fate of our universe, and answer questions that would be impossible to investigate through observation alone. Scientists then input the fundamental constants that govern our universe. The gravitational constant that determines how strongly masses attract each other. The density and properties of dark matter, which we'll discuss more in a moment. The cosmological constant that drives cosmic expansion. And many other parameters that define the physics of our cosmos. The implications are staggering. These simulations aren't just academic exercises or pretty visualizations. They're powerful scientific tools that allow us to test hypotheses about cosmic evolution that would be impossible to verify through observation alone. After all, we only have one universe to observe, and we can't rewind time or change initial conditions to see what would happen differently. But in a simulation, we can do exactly that. We can adjust the amount of dark matter, change the rate of cosmic expansion, or modify the strength of fundamental forces, and then watch what unfolds over billions of simulated years. And as we explore these digital universes, we'll confront an unsettling question. If we can simulate a universe, could our universe itself be a simulation? Let me tell you about some landmark simulations that have revolutionized our understanding of the cosmos. The Millennium Simulation, completed in 2005, tracked more than 10 billion particles through cosmic history, creating a virtual universe over 2 billion light-years across. The Illustris simulation, completed in 2014, represented a major leap forward because it included not just dark matter, but also the complex physics of ordinary matter. It incorporated gas dynamics, tracking how gas heats, cools, and flows through space. It included supermassive black holes at galaxy centers, modeling how they grow by consuming surrounding matter. It simulated feedback processes where stars and black holes inject enormous amounts of energy back into their surroundings through stellar winds, supernova explosions, and powerful jets from black holes. These feedback processes are crucial because they regulate star formation, preventing all the gas in a galaxy from turning into stars too quickly. The simulation produced virtual galaxies that looked remarkably similar to real galaxies observed by telescopes, matching not just their overall appearance, but also detailed properties like their sizes, shapes, colors, and the amount of stars they contain. This was a stunning validation that we truly understand the physical processes that shape galaxies. More recently, the Illustris TNG project, completed in 2018, expanded on this success with even higher resolution and improved physics. This ambitious suite of simulations created multiple simulated universes of different sizes, the largest spanning over 1 billion light-years across, allowing scientists to study everything from individual galaxies to the large-scale structure of the cosmos. What makes Illustris TNG particularly remarkable is its ability to track not just dark matter, but also the complex behavior of ordinary matter, including gas cooling, star formation, stellar evolution, and the powerful feedback from supernovae and supermassive black holes. The virtual galaxies it produced match real galaxies in detailed properties like their shapes, sizes, colors, and internal structure. This remarkable agreement between simulation and observation across multiple independent measurements gives us confidence that we truly understand the fundamental processes driving cosmic evolution over billions of years. The Illustris simulation, completed in 2014, took things to an entirely new level. It didn't just simulate dark matter and gravity, it also included the complex physics of gas dynamics, formation supermassive black holes at galaxy centers, and the feedback processes where stars and black holes inject energy back into their surroundings. This feedback is crucial because it regulates star formation, preventing all the gas in a galaxy from turning into stars too quickly. The simulation produced virtual galaxies that looked remarkably similar to real galaxies observed by telescopes. Finally, there's cosmic expansion, driven by dark energy, which makes up about 68% of the universe's total energy density. Dark energy is even more mysterious than dark matter. It acts like a kind of anti-gravity, causing the expansion of space itself to accelerate. This expansion affects how structures grow over cosmic time. In the early universe, when matter was denser, gravity dominated and structures grew rapidly. But as the universe expanded and dark energy became more important, structure growth slowed down. Understanding this interplay between matter trying to clump together and dark energy trying to pull everything apart is crucial for understanding cosmic evolution. Let me tell you about some of the landmark simulations that have revolutionized our understanding of the cosmos. The Millennium simulation, completed in 2005, was a groundbreaking achievement. It tracked more than 10 billion particles through cosmic history, creating a virtual universe over 2 billion light-years across. This simulation revealed how dark matter halos form and merge over time, providing the gravitational wells where galaxies can form. It showed us the hierarchical nature of structure formation, where small structures form first and then merge to create larger ones, a process that continues throughout cosmic history. But simulations must also solve the equations of hydrodynamics to track how gas flows, heats, and cools. They must model magnetic field evolution, which affects how gas collapses to form stars. They must simulate the formation and growth of supermassive black holes, which can contain millions or billions of times the mass of our sun. And they must model feedback processes, where energy from stars and black holes affects the surrounding gas, regulating future star formation. More recently, the illustrious TNG project expanded on this work with even higher resolution and more sophisticated physics. The TNG simulations can follow the formation of individual galaxies in exquisite detail, showing how gas flows in and out of galaxies, how stars form in spiral arms and galactic disks, and how supermassive black holes grow and influence their host galaxies. Another major project is the EAGLE simulation, which focused on reproducing the observed properties of galaxies across cosmic time. By carefully calibrating the simulation's parameters, EAGLE produced virtual galaxies that match real galaxies in their masses, sizes, colors, and star formation rates. These simulations are so important because they provide a crucial link between theory and observation. They allow us to test whether our understanding of fundamental physics can actually produce a universe that looks like ours. When simulations successfully reproduce what we observe, it gives us confidence that we're on the right track. When they fail, it tells us something is missing from our theories, pointing the way toward new physics and deeper understanding. Building blocks of creation. It's not magic that makes these universe simulations work. It's algorithms, sophisticated mathematical procedures that break down the complex physics of the cosmos into steps a computer can execute. Breaking down the core computational challenges of simulating billions of particles reveals just how difficult this endeavor truly is. The fundamental problem is what's called the n-body problem, calculating the gravitational force between every pair of particles in the simulation. If you have n particles, there are n times n minus 1 divided by 2 unique pairs, which means the number of calculations grows as the square of the number of particles. For a simulation with 10 billion particles, that's roughly 50 quintillion pairs to consider. Doing this calculation directly for every time step would be impossibly slow, even for the fastest supercomputers. The supercomputers used for these simulations are among the most powerful machines on Earth, with thousands of processors working in parallel, require millions of processor hours, hundreds of terabytes. Despite these enormous computational challenges, these simulations provide invaluable insights, scientists' different parameters observations. One of the most fascinating aspects is watching how incredible complexity emerges from relatively simple rules. The simulations start with just basic physics, primarily gravity and the expansion of space, along with initial conditions representing tiny quantum fluctuations. Yet from these beginnings, they produce galaxies, and cosmic that with stunning accuracy. Within these galactic disks, the story continues at smaller scales. Gas clouds collapse under their own gravity to form stars. The most massive stars live fast and die young, exploding as supernovae after just a few million years. These explosions enrich the surrounding gas with heavy elements like carbon, oxygen, and iron, essential for planets and life. Meanwhile, at the centers of galaxies, supermassive black holes grow by consuming surrounding matter. As material spirals into these black holes, it heats up and releases tremendous energy, creating brilliant quasars that can outshine entire galaxies and drive powerful winds that regulate star formation. Galaxies don't evolve in isolation. They collide and merge with neighbors in slow motion cosmic ballet, triggering intense bursts of star formation and dramatically reshaping their structures. All this complexity emerges naturally from the physics we've programmed into the simulation without any special instructions to create galaxies or stars. It's emergence in action, simple rules producing complex outcomes. What do we learn from? Despite these enormous computational challenges, these simulations provide invaluable insights that would be impossible to obtain any other way. By running multiple simulations with different parameters, scientists can explore different possible universes and determine which parameters best match our observations. This is like having a cosmic laboratory where we can test our theories by creating alternative realities and comparing them to the universe we actually inhabit. Each simulation run teaches us something new about how sensitive cosmic structure is to the fundamental constants of nature. These simulations reveal something profound about the nature of reality itself. They demonstrate the extraordinary power of emergence, how the entire magnificent complexity of the cosmos, with its billions of galaxies, intricate cosmic web, and potential for life, arises inevitably from just a handful of fundamental physical laws and initial conditions. We don't need to program instructions for creating spiral galaxies or galaxy clusters. These structures emerge naturally, spontaneously, from the underlying physics. This tells us something deep about our universe. Complexity doesn't require complex rules. Simple laws, operating across vast scales of space and time, are sufficient to generate everything we see. What do we learn from? But gravity isn't the only challenge. Simulations that include ordinary matter must also solve the equations of hydrodynamics, describing how gas flows, compresses, heats, and cools. Gas can form shock waves, turbulent flows, and complex instabilities. It can cool and condense to form stars, or be heated and expelled by supernova explosions. Modeling all of this requires solving partial differential equations on a grid or using particle-based methods like smoothed particle hydrodynamics. Then there's radiative transfer, tracking how light and radiation propagate through the universe, heating some regions and ionizing others. There's magnetic field evolution, chemical enrichment as stars produce heavy elements and distribute them through supernova explosions, and the formation and growth of black holes. Each of these physical processes requires its own algorithms and adds to the computational burden. The challenge is not just implementing each piece of physics correctly, but making sure they all work together in a consistent, stable way over billions of years of simulated time. The sheer computational power required to run these simulations is staggering, which is why supercomputers are the only way to even begin these cosmic endeavors. A modern universe simulation might require millions of processor hours, meaning if you ran it on a single processor, it would take millions of hours or more than a century to complete. By distributing the calculation across thousands of processors working in parallel, the time can be reduced to weeks or months. But this parallel computing introduces its own challenges. The The simulation domain must be divided among processors, with each processor responsible for calculating the evolution of particles in its assigned region. But particles don't stay put. They move according to the forces acting on them, potentially crossing from one processor's domain to another. This requires constant communication between processors, exchanging information about particles near boundaries and synchronizing the calculation. The supercomputers used for these simulations are among the most powerful machines on Earth. They contain thousands or tens of thousands of processors, terabytes or petabytes of memory, and sophisticated high-speed networks connecting all the components. The energy consumption is enormous, often measured in megawatts, equivalent to the power consumption of a small town. The data generated is equally massive. A single large simulation can produce petabytes of data, requiring vast storage systems and sophisticated data management strategies. Scientists can't save the state of every particle at every time step. The data would be overwhelming. Instead, they save snapshots at intervals, capturing the state of the universe at key moments in its evolution. Even these snapshots are huge, and analyzing them requires additional computational resources and specialized visualization software. The cost of running these simulations is substantial, not just in terms of computer time and energy, but also in human resources. Teams of scientists, programmers, and engineers work for years developing the simulation codes, debugging them, optimizing them for specific supercomputer architectures, and analyzing the results. Despite these challenges, the investment is worthwhile because these simulations provide insights that can't be obtained any other way. There are only method of testing cosmological theories over billions of years and across billions of light years of space. They allow us to explore parameter space, asking what-if questions about the universe. What if dark matter had different properties? What if the cosmological constant were larger or smaller? What if the initial density fluctuations had a different amplitude? By running simulations with different parameters, scientists can map out which combinations produce universes that look like ours, and which produce radically different outcomes. These simulations serve as powerful laboratories for testing our theories about cosmic origins and evolution, providing profound insights that reshape our understanding of the universe. Dark matter represents one of the greatest mysteries in modern physics, an invisible substance that dominates the mass of the universe, yet remains frustratingly elusive. Dark matter is invisible because it doesn't emit, absorb, or reflect light or any other form of electromagnetic radiation. It interacts only through gravity and possibly through extremely weak forces we haven't yet detected, making it incredibly difficult to study directly. We infer its existence from multiple independent lines of evidence. Galaxies rotate too fast to be held together by visible matter alone. They should fly apart unless there's additional invisible mass providing extra gravitational glue. Galaxy clusters bend light from background objects more than their visible matter can account for, revealing the presence of dark matter through gravitational lensing. In fact, dark matter makes up about 85% of all matter in the cosmos, meaning the atoms that make up stars, planets, and everything we can see represent only a small fraction of total matter in the universe. In simulations, we can explore how different properties of dark matter affect cosmic structures in ways impossible to test through observation alone. Cold dark matter, moving slowly compared to the speed of light, produces the hierarchical structure we observe in the real universe, where small structures form first, then merge to create larger ones in a bottom-up process. We can also test alternative theories like warm dark matter, which moves faster and would smooth out structure on small scales, or self-interacting dark matter, which could collide with itself and alter the density profiles of galaxy centers. By comparing these different scenarios to observations of how galaxies are distributed and how they behave, simulations help us narrow down the properties of this mysterious substance and guide experimental efforts to detect dark matter particles directly. Dark energy is even more mysterious than dark matter, a strange form of energy that permeates all of space and causes the expansion of the universe to accelerate. Discovered in 1998 through observations of distant supernovae, dark energy makes up about 68% of the universe's total energy content. In simulations, we can explore how dark energy works against gravity, making it harder for new structures to form as the universe ages and cosmic expansion accelerates. By varying the strength of dark energy in our simulations, we can predict how it affects the growth of galaxy clusters and the overall architecture of the cosmic web. These simulations also allow us to peer into the far future and predict the ultimate fate of our universe based on different models of dark energy's behavior. If dark energy continues to accelerate cosmic expansion at its current rate, the universe faces a cold, lonely future in what cosmologists call the Big Freeze or heat death. Over trillions of years, galaxies will recede beyond our cosmic horizon, carried away by expanding space faster than light can travel between them. The universe will become increasingly dark and empty. Stars will exhaust their fuel and die, and eventually even black holes will slowly evaporate through Hawking radiation over timescales of 10 to the 100 years or more, leaving behind only a thin soup of elementary particles in an ever-expanding, ever-cooling void. Dark matter represents one of the greatest mysteries in modern physics, and simulations have been crucial in helping us understand it. Dark matter is invisible matter that doesn't emit, absorb, or reflect light. It interacts with ordinary matter only through gravity, making it incredibly difficult to detect directly. We infer its existence from multiple lines of evidence. Galaxies rotate too fast to be held together by the gravity of visible matter alone. They should fly apart, yet they remain intact. Galaxy clusters contain far more mass than we can see in stars and gas. Gravitational lensing, where massive objects bend light from distant sources, reveals the presence of enormous amounts of invisible mass throughout the universe. In fact, dark matter makes up about 85% of all matter in the cosmos, meaning the atoms that make up everything we can see, stars, planets, and ourselves, represent only a small fraction of the universe's total matter content. In simulations, we can explore how different properties of dark matter affect the formation of cosmic structures. Cold dark matter, which moves slowly compared to the speed of light, produces the hierarchical structure we observe in the real universe. In these simulations, small structures form first, then merge to create larger ones, building up galaxies, galaxy groups, and massive galaxy clusters over billions of years. This bottom-up assembly matches what we see in the cosmos. We can also test alternative theories like warm dark matter, which moves faster and would smooth out small-scale structures, or self-interacting dark matter, which could solve certain puzzles about galaxy cores. By comparing these different scenarios to observations, simulations help us narrow down the properties of this mysterious substance that dominates the universe's matter content. Dark energy is even more mysterious and perplexing than dark matter. Discovered in 1998 through observations of distant supernovae, dark energy appears to be a property of space itself that causes the expansion of the universe to accelerate. It makes up approximately 68% of the universe's total energy content, making it the dominant component of the cosmos. Yet we have no fundamental understanding of what it actually is. In simulations, we can explore how dark energy affects the growth of cosmic structures over time. As the universe expands and dark energy becomes more dominant, it works against gravity, making it harder for matter to collapse and form new structures. This means that in the distant future, structure formation will essentially cease. Simulations allow us to test different models of dark energy, from Einstein's cosmological constant, which remains perfectly uniform throughout space and time, to more exotic theories where dark energy's strength changes over cosmic history. Perhaps most profoundly, these simulations allow us to peer into the far future and predict the ultimate fate of our universe. This is the principle of emergence, where complex patterns and structures arise from the interaction of simple components following simple rules. In the early stages of a simulation, the tiny density fluctuations begin to grow through gravitational instability. Slightly denser regions attract more matter, becoming denser still, while less dense regions lose matter and become voids. This process is self-reinforcing, a positive feedback loop that amplifies small differences into large structures. As matter collapses into denser regions, it doesn't fall straight in. Conservation of angular momentum means that any small rotation in the initial conditions gets amplified as matter contracts, causing it to spin faster like a figure skater pulling in their arms. This rotation causes the collapsing matter to flatten into a disk, which is why so many galaxies are disk-shaped spirals. Within these disks, further instabilities arise. Spiral density waves form regions of enhanced density that rotate through the disk like the arms of a spiral galaxy. Gas flowing through these density waves gets compressed, triggering star formation. The massive stars that form live fast and die young, exploding as supernovae and enriching the surrounding gas with heavy elements. These explosions also inject energy into the gas, heating it and driving powerful winds that can blow gas out of the galaxy entirely. Meanwhile, at the center of the galaxy, matter falling toward the supermassive black hole releases enormous amounts of energy, creating jets and winds that can affect the entire galaxy and even the surrounding intergalactic medium. All of these processes interact in complex ways, creating feedback loops that regulate star formation and galaxy growth. On larger scales, galaxies don't exist in isolation. They're embedded in massive dark matter halos and cluster together along filaments, forming the cosmic web. Galaxies can merge when they encounter each other, triggering bursts of star formation and transforming their shapes. Small galaxies can be torn apart by tidal forces from larger neighbors, their stars scattered into streams and shells. Gas can be stripped from galaxies as they move through the hot gas in galaxy clusters. All of this complexity, all of these diverse phenomena, emerge naturally from the simulation without being explicitly programmed in. The simulation doesn't have a rule that says form a spiral galaxy here or create a galaxy cluster there. Instead, these structures arise inevitably from the underlying physics. This emergence is powerful evidence that we understand the fundamental processes shaping the universe. It also reveals something profound about the nature of complexity itself. You don't need complex rules to create complex outcomes. Simple rules, operating over vast scales of space and time, are sufficient to generate the rich, structured universe we inhabit. So what do we actually learn from running these universe simulations? The insights are profound and multi-layered, touching on everything from fundamental physics to the deepest philosophical questions about existence itself. First and foremost, these simulations teach us about the extraordinary power of emergence. We witness how the entire magnificent complexity of the cosmos, with its billions of galaxies, intricate cosmic web, and diverse structures, arises naturally from just a handful of fundamental physical laws and simple initial conditions. We don't program galaxies into existence. We don't tell the simulation where to place galaxy clusters or how to form spiral arms. Instead, all of this complexity emerges spontaneously from gravity, the properties of matter and energy, and the expansion of space. This is a profound lesson about the nature of reality itself. It suggests that the universe doesn't require infinite complexity at its foundation. Simple rules, operating over vast scales of time and space, are sufficient to generate everything we observe. Second, simulations provide an unprecedented laboratory for testing our understanding of fundamental physics. We can validate whether our theories of gravity, dark matter, and dark energy actually produce a universe that matches observations. When simulations successfully reproduce the distribution of galaxies, the properties of the cosmic web, and the evolution of structures over billions of years, it gives us confidence that we're on the right track. When they fail, when the simulated universe doesn't match reality, it tells us something crucial is missing from our theories, pointing the way toward new physics and deeper understanding. This ability to test cosmological theories across billions of years and billions of light years of space is something we could never achieve through observation alone. Third, these simulations force us to confront profound philosophical questions about the nature of reality and our place in the cosmos. If we can create entire universes inside computers, universes that evolve according to physical laws, and potentially could even give rise to conscious observers, what does that say about our own existence? Are we fundamentally different from the digital entities in our simulations, or are we perhaps ourselves inhabitants of a higher level simulation? The simulation hypothesis isn't just philosophical speculation anymore. It's a testable scientific question. We can look for signatures in our universe that might reveal its computational nature, glitches in the code, limits to physical resolution, or patterns that suggest underlying algorithms. Finally, these simulations reveal both the power and the limits of human knowledge. On one hand, it's extraordinary that we can recreate the evolution of the entire universe on computers, that we understand the fundamental forces well enough to simulate billions of years of cosmic history. On the other hand, the simulations also highlight how much we still don't know. We don't understand what dark matter actually is, despite knowing it dominates the universe's mass. We have no fundamental theory of dark energy, even though it makes up most of the universe's energy content. We can't yet simulate the formation of life or consciousness, even though these phenomena presumably emerge from the same physical laws that govern everything else. These gaps in our knowledge aren't failures, they're invitations pointing toward the frontiers where the next great discoveries await. As we reach the end of our journey through these digital universes, it's worth reflecting on what we've discovered. We've seen how scientists can create entire cosmos inside computers, watching billions of years of evolution unfold in months of computation. We've witnessed the power of emergence, how simple physical laws give rise to the magnificent complexity of galaxies, stars, and the cosmic web. We've explored how these simulations help us test our theories about dark matter and dark energy, those mysterious components that dominate the universe yet remain frustratingly elusive. And we've confronted the unsettling possibility that our own reality might itself be a simulation, a digital construct running on hardware we can't even imagine. But perhaps the most important lesson is this: the universe is knowable. Despite its vast scale, its 14 billion year history, and its countless mysteries, we can understand it. We can reduce its complexity to fundamental principles, encode those principles in mathematics, and use them to recreate cosmic evolution. This is an extraordinary achievement of human intellect and curiosity. Yet even as we celebrate how much we've learned, we must remain humble about how much remains unknown. The nature of dark matter and dark energy, the origin of the universe itself, the possibility of other universes beyond our own, the potential for life and consciousness to emerge elsewhere in the cosmos, these questions still await answers. The simulations we've explored today are not endpoints. They're tools, powerful instruments that help us ask better questions and design better experiments. As our computers grow more powerful and our understanding deepens, these digital universes will become ever more sophisticated, revealing new insights about the cosmos and our place within it. And perhaps one day we'll create a simulation so detailed, so complete, that it gives rise to conscious observers who look up at their own simulated sky and wonder, as we do whether they might be living in a simulation themselves. In that moment, we'll have come full circle, creating universes that mirror our own existential questions. Until then, we continue the ancient human quest to understand reality, armed now with the most powerful tool ever devised, the ability to create universes and watch them evolve, to test our theories against digital cosmos, and to glimpse through mathematics and computation the fundamental nature of existence itself. Until next time, remember to look up, but remember we are the way the universe can understand itself, so make sure to look within yourself.